Remember last week we did the factoring, so remember your factoring assignment is due next Monday with this one, section 3.1. We're just covering section 3.1 today, or tonight. I will try and get those tests graded as soon as I can and entered into Canvas so that you know how you did as soon as possible. One thing that I will mention again, well, two things I'll mention again. First of all, make sure you're working through your homework, and some of you have been very diligent with that and working through that, so that's great. And some have been not quite so diligent. So make sure you're working through your homework, because that's, again, the whole point of that homework is to get practice for your test. Secondly, remember that review that I put in there with you, the test review. The questions that you see on your test are very, very similar to the review problems. The wording, I tried to keep the wording relatively similar so that the words are not, so that the wording of the problem is not confusing because you've seen it already. So please make sure you check that out. I know a few people did, but not as many as probably should. So make sure you take a look at that. I also give you some bonus points for doing it. So make sure you're checking that out before those tests when you come in. That way you'll know ahead of time, hey, I struggled a lot with this type of question, even though I tried it a few times, I still wasn't getting it. Those are the types of things that when you come in, when I'm saying, hey, do you have questions? Those would be the types of things that you should probably ask about. Okay, does that make sense? And for those of you guys who just missed that, you'll have to just listen to the video at the first 5 minutes and a couple minutes and hear what I said. So we are going on to section 3.1, and we're going to talk about, we're introducing the idea of polynomial functions. And we're going to focus at the beginning here on what are called power functions. And so a power function is a function that can be represented in the form of just x raised to a power. So f of x equals x raised to some power p. And that power p, okay, so our base is a variable, but the exponent p is a positive integer. So anything 1, 2, 3, 4, 5, but no fractions, no decimals, no negatives, is going to be a positive integer. I just realized I didn't hook this up. But anyway, that is what a power function is. And we're going to look at some of the characteristics of these power functions. And that's going to help us as we learn some more things about polynomials in general. Uh-oh. My battery might be dead. There we go. Okay, so if you think back to our toolkit functions, way back from the first week and the first couple weeks, we spent a lot of time kind of talking about them and discussing them. So our toolkit functions, some of them are power functions. So we want to look back through these power functions. So here's the first one. F of x equals x, and that is because it is x raised to the first power, right? So the exponent on the x is an integer, and that is a power function. So we're going to be talking about these, and we're going to be looking at characteristics, okay? So f of x, just a straight line going through 0, and that is our first most basic power function. The next one, as you may guess, is f of x equals x squared with a 2 there. And you'll notice that you've got the parabola shape here, as we talked about. Actually, we'll be talking more about that this chapter, but we talked about it back in the first chapter when we were talking about the power function, or about the toolkit functions. And then the last main one that we have in our toolkit functions is the cubic function, f of x equals x cubed, and you'll notice that looks like this. So some interesting patterns occur if we keep looking at these toolkit functions, these power functions. And the first question we want to look at, and we'll go back and kind of talk about them, but what point or points do the toolkit power functions all have in common? So as we go back and we look at them, and I should have these lined up so that when I circle it, it stays there. But you'll notice 0, 0 is in this one, 0, 0 is in this one, and 0, 0 is in this one. So the first point that is part of all of those functions is the point. Oh yeah, these are the dead ones. I should have thrown them away. Where did I have one? Here it is. There's 2 up here. So the first one is 0, 0. That's in all of them. Okay. A second point that's in all of them is this one right here. You'll notice 1, 1. If we go back, 1, 1, and 1, 1. That's in all of them. Okay, so those 2 points are in all of them. And then we have a separation here. So I'm going to call this the odd and the even, and I'll tell you what that means in a second. But first, when we think of that, that is x to the first power. If the exponent is odd, so odd exponent, the third point that's going to be in those is this point down here, -1, -1. Okay, and so you see it there. This one's, whoops. This one is even, so we're not talking about that one, but it's right here as well, -1, -1. So if it's an odd exponent, this point will be in each of them. The -1, -1. But when it's an even exponent, it's not -1, -1 down here. It's going to be -1, +1. So even exponent, -1, +1. Okay, but that combination of those 3 points is always going to be in our power functions. And if you think about why, if I have 0 and I raise it to whatever power, isn't it always 0? Even to the 100th power. Same thing with 1. 1 raised to any power is always 1. When you have an odd exponent, -1 raised to that odd exponent is going to be -1. But when you have an even exponent, -1 raised to that even exponent will be +1. So that's going to give us some things to work with as we look at these power functions and then more generally the polynomial functions. Okay, so those are the points that those toolkit power functions have in common. So these are the 2 that all of them have in common, and then these are the 2 special ones, depending on if it's even or odd exponent. Okay, so let's take a look at this and get a little bit more information here. What do you notice about all of these? First thing I'm going to mention is you've got x squared, you've got x to the 4th in the green, and then x to the 6th in the blue. What do you notice about the general shapes of all of these? They kind of look like quadratics, right? Which the simplest one is a quadratic, right? It's a parabola, okay? But notice they all go through 0, 0. They all go through 1, 1, and -1, 1, right? Because they all have even exponents, but also because of the even exponents, they all go up on the left side and up on the right side. Do we see that? They're both going up, all 3 of them are going up on the left, or up on the right and up on the left. Okay, and that's in your notes, and you may want to make that note. If it's an even power, they go up on the left-hand side and up on the right-hand side. That's always true. So if I gave you some generic x to the 24th power as my function, it would look similar to these in that it goes up on the right and up on the left. Okay. Now when we look at the odd powered ones, what do you notice? That's different. I mean, the same as each other, but different from the other ones.
They go up and down.
Yeah, they go up over here on the right, and they're down over here on the left. Okay, and these power functions are something that we kind of want to get in our memory. Okay, so odd power, 3, 5, 7. The exponent is odd. If that is true of the power function, they will be down on the left, and they will be up on the right. Okay, and that's going to be important because we're going to use that general characteristic of this picture and this picture to help us when we talk about something called end behavior of general polynomials. Because end behavior is talking about what happens on the far left-hand side and what happens on the far right-hand side. Okay? So that leads us to our more general polynomials. And polynomials, a polynomial function with a degree of n is a function of this form. And this is really complicated looking. It's really not nearly as complicated as it may seem. Okay? But here's the idea. First of all, n has to be a non-negative integer, and a sub n can't be 0. So in other words, this term has to be here. The rest of the terms may or may not be there. But here's the idea. The degree, n, is simply the highest exponent that you see in the function. Okay? So if we saw some of those, like on the last one where it was x to the 7th, 7 would be the degree. Or when it was x to the 4th, 4 would be the degree. Whatever the highest power is, that's the degree of the polynomial. Okay? And all these a's mean, these a's are just numbers. They just represent numbers. It's just we don't know how long the polynomial is or how short. So we have these numbers just generically written as a's, but they just represent numbers. And then you've got x raised to a power, x raised to a lower power, and a lower power and lower power until finally get down to just a number at the end. Okay? And we will do some examples. Actually, we have already been doing these. For instance, has anybody seen anything ever in their whole life, like in the last 2 weeks, that looks like this? Or like in the last 60 minutes, because that was the starting point of one of the questions on your test. Do you see that this is actually a polynomial function? It has two pieces. This is 3x raised to the first power, so its degree is 1, and then plus 3. So we've been doing very small versions of polynomial functions so far. Okay, we're going to extend this to not just 2 pieces, but maybe 3 or maybe 4. Okay, but that's what we're going to be working on as we go through this stuff tonight. So the numbers, as I already mentioned, the numbers, the a sub 0, a sub 1, a sub 2, those are just numbers. Those are called coefficients of the polynomial. Okay, so when you, and again, I don't typically test on terminology. I'm not going to give you like match the term with its definition. But when we use the word coefficient, you need to know what we're talking about, right? The coefficient just means number in the function, polynomial function. Okay. Each term of the polynomial is any one piece of the sum that has a number in front of it, an a value, a sub I they call it, and then x sub I. The i's just mean it has a power and it has a number. Okay, so here's what that's going to look like. This piece right here, remember how I call them pieces when I was talking about the line? That piece is a term. This piece is another term. This, whoops, there's nothing there. This piece is another term. This actually goes all the way to there. So when I do that example of y equals 3x plus 3, 3x is one term, and then 3 is another term. Each of those are terms. So that one has 2 terms. Okay. Every time you see a plus or a minus, you're going to have another term. So we're going to be looking at those. Okay. Any questions on that so far? I mean, there's not really, we haven't done anything really yet. It's just more informational. But any questions so far on anything that you're not sure about? All right. So the degree of a polynomial, and we already kind of mentioned this, is the highest power of the variable that occurs in the polynomial. So that's, if we put it in what is called standard form, we start with the biggest power down to the smallest power. So the degree should be this one here at the beginning, if it's in standard form. Because when we write our answers, that's what we want. Biggest one at the beginning, smallest one at the end. Okay, so that is the degree of the polynomial. The leading term, leading meaning the one in the front, if it's in standard form. So the leading term is the term containing the highest power of the variable. And that would mean it's the term with the highest degree. And again, if we put it in standard form, that's going to be the first one. The number a sub n is called the leading coefficient. So again, the leading one, that's the first one, the one in the front, and then the coefficient is the number. and that's the coefficient of the leading term. So again, a couple more words to look at there, vocabulary. But when we talk about the leading, we're talking about this first one, the one that has the highest power. All right, so identify the degree, the leading term, and the leading coefficient of these polynomials. So the first thing you always, so the first thing I would suggest that you do is put it in standard form, which means we're going to start with the highest power and go down to the lowest power. So what is the highest power that you see here? A 3, and it's this one right here, correct? So this negative 4x cubed has to go to the front. The negative goes with the 4, and that goes with the x cubed. What's the next highest power that you see? The 2 right here. So this one is the next one, and that plus goes with, so plus 2x squared. And the last is going to be a 3. And that's a plus 3 because it's a positive 3. The sign in front of the number goes with that number. So we have, this isn't part of the question, but how many terms do we have here? 3 terms, right? And so what is the degree of our polynomial? That's the leading term. But the degree is just this power on the first one. So the degree is just 3. So the degree is 3. Now you were one question ahead of me. What is the leading term? The leading term is this negative 4x cubed. Okay. And then finally, what is the leading coefficient? Okay, now remember the leading coefficient is going to be part of the leading term. It's just the number part
2
of the leading term.
Oh, negative 4.
It's going to be the negative 4. Okay? So the degree and the leading coefficient are both part of that leading term. That's why the leading term is so important. Okay, does that make sense on that example? Any questions before we go on to another one? All right, so degree is 3, leading term, got that. All right, next one for the g function here. And notice this one is already in the right order, right? From the highest power to the lowest power. So again, let's start with our degree. What is the degree of this one? 5. I don't know who said it, but you were correct. 5 from right here. That's the highest power. What is the, I'm just going to abbreviate the leading term, LT. 5t to the 5th power. And again, when you put that in order, it's the first one. And notice they don't have to be x's. We had t's and we had x's. It's fine. Whatever the variable is. And then the leading coefficient. What is that going to be? Just 5. And that's this part. The coefficient, the number part in the front. Okay? Does that make sense? So some terminology there, but it's not difficult as long as you practice it a little bit and get familiar with those words. Okay? How about this one? Now again, this one is not in the correct order or standard form. I say the correct order because we really want it to be in that order, standard form. So how would we rewrite this one to begin? H of P equals, what would we put first? Yep. And we don't have to put the 1, but it's automatically there. But negative 1p cubed goes, what goes after that? 6p, so that would be plus 6p because it's a positive 6. Then last is minus 2. Notice how those are different because this one has a p and this one does not. Okay, so once again, we still have 3 terms. Everyone has had 3 terms so far. What is our degree this time? 3 is correct because it's right here. Okay, next, what is our leading term? Negative p cubed. Yep. Negative p to the 3rd power. And then finally, our leading coefficient. And actually, you said this one before. What is it? -1. Remember, the 1 is automatically there. So if you just see the negative, the 1 is automatically there. Or if there's no negative and no number, it's a positive 1. Okay? Any questions on that? All right. And it looks like we're good there. So we have something when we're talking about these polynomials that is called the leading coefficient test. Now I want us to think back to our power functions. And let's start. We started with the even ones. What did all of the even ones basically look like? A U. They were up on the left and up on the right, correct? That's what all the even ones basically look like. That make sense? And what did all of the odd ones basically look like, other than to the first power? But any of the other ones, 3, 5, or 7, what did they look like? What? Like a snake. I'm going to fill in the blank. It was down on the left, and then it would go up on the right, correct? That's kind of what it looked like. And that's going to be important because we're going to use that right here on this leading coefficient test. So, end behavior. When we talk about end behavior, all we're talking about is what happens on the far left-hand side and the far right-hand side. Okay? That's all that end behavior talks about. What happens way over here on the left and way over here on the right. So, the end behavior of the polynomial is determined by its degree and the sign of the leading coefficient. The two things we have to look at when we're looking at the degree is the degree even or is it odd? Which of these two groups is it going to share some characteristics with? Okay? And so that's what we're going to look at first. So this first one is odd degree. Okay, so we're kind of looking at this one, odd degree, with this a sub n, remember that's the symbol for the leading coefficient. So it has a positive leading coefficient, it's greater than 0. Here's an example of what that might look like. Oh, sorry, first some notation. More notation before we get started. So if we see this, symbolism here, x with an arrow and negative infinity, that means that if you think about x's approaching, that the arrow means approaching. So if x's are approaching negative infinity, that means they're getting bigger and bigger negative numbers. They're going to the left. So when we talk about this, we're talking about the left side of the graph, the left side end behavior. Okay. When we look at x approaching positive infinity, that's the positive values getting bigger and bigger and bigger. That means we're talking about the right side of the graph. So that's the right side end behavior. And we will always have the two. We're always going to be talking about the left side and the right side. Okay. Then, if we talk about f of x, I don't know why I have these switched around, but f of x approaching infinity means the function values are going up and getting bigger and bigger positive. So that means the graph is going up. Okay. If we have f of x approaching negative infinity, that means the graph is going down. So we're always going to look at the left and right, and this is how we will describe it. The graph is either going to go up or it's going to go down, just like these do. They either go both up or one up and one down. Okay? Everybody got that written down? Is it on your paper already, I would guess? Okay. So just so you understand what that means. So here's our first example. If we have an odd degree and a positive leading coefficient, do you see that the end behavior, what happens over here and what happens over here, mimics that? It's the same as that. It's down on the left and up on the right. Does that make sense? We're not talking about what happens in the middle right now, because other things are happening in the middle, but we're just talking about what happens on the far left-hand side and what happens on the far right-hand side. So look at our description here. As, that's the dead one. Let me get something that we can do here. So as x approaches negative infinity, remember this means the left side. So we're talking about the left side of the graph. And what is happening on the left side? Well, we can see that it's going down, just like we would expect from up here. And so when it's going down, and sometimes we'll see f of x or sometimes we'll see y, they're kind of interchangeable. But you see y is approaching negative infinity. That means it's going down. Okay. Now over here, as x approaches positive infinity, that means we're talking about the right side of the graph. And we can see what's happening over there. It's going up. So the way we describe that is y is approaching positive infinity. It's going up. Okay, so when we're describing what happens, we're going to say y approaches negative infinity or y approaches positive infinity, depending on if it's going up or down. Okay, these parts, in fact, all of this will pretty much always be the same from here to here, because we're always going to say what's happening on the left, this is what it's doing, and we just fill in the infinity or negative infinity, depending on if it's up or down. The same thing will happen over here. All of this will always be the same, and we'll just put in an infinity or negative infinity, depending on if it's going up or down. Okay, so that's the first one. Odd degree, positive leading coefficient. Now, we talked about transformations and translations and different things that we can do to graphs. What do you think will happen if we put a negative in as the leading coefficient? Remember what happens when we put a negative in there in the front? It's been a little while, but
It turns upside down.
yeah, it turns upside down. It reflects over the x-axis, so it flips up and down. So if we think about that, the odd degree looks like this, but what happens if we flip it? Do we see now it would be up over here on the left and down over on the right if it gets flipped? And that's exactly what happens. If we have a negative leading coefficient, now it gets flipped and it's up on the left and down on the right. Okay, and again, don't let this terminology, this is exactly the same as x approaches negative infinity, talking about the left-hand side. What is the function doing? It's going up, positive infinity. Okay, as x approaches positive infinity, that means you're talking about the right-hand side. What is the function doing? It's going down, negative infinity. Okay, so really, if we can keep this picture right here in our minds, or these two pictures in our minds, it helps us to figure these out as long as we remember, is it reflected or not? And it's reflected if there's a negative leading coefficient, and it's not reflected if there's a positive. Anybody need any more time for that? By the way, there's probably space there for you to draw pictures. I try to leave space there. I think I probably have space there, but if you want to draw the pictures, that's fine. If you don't want to, that's fine as well. You can always go back and look. The slides are on Canvas. Okay. So let's go ahead and go to the next one. So the next one's going to be even, positive leading coefficient. So what do you think it's going to look like in general? Does it make sense? It's going to look kind of like this. Even degree, positive leading coefficient. And that's exactly what happens. Again, the middle we're not worried about, but we're just talking about the ends. Left side, right side, up and up. Right? Left side is up, right side is up, just like this. Just like all those pictures that we saw, all those even degreed power functions. What do you think is going to happen if we put a negative in front of it? It's going to flip, right? And so what's going to happen? They're both going to be going down. Okay? And again, we're not worried about the middle right now. We're just worried about the ends. What's happening on the ends? And on the left-hand side and the right-hand side, they're both going down. So you see that as x approaches negative infinity, negative infinity. Down. As x approaches positive infinity, negative infinity, down. Okay? And that's the description that we're pretty much looking for every time. And I think if I remember right, your homework has all of this, and they have a box for you to put this in. Either infinity or negative infinity is what you're going to be putting in those spots. Okay? And it's all based on, do we think it's going up or do we think it's going down? So let's try some of these. And again, like I say, this is how, if I remember right, this is how I think it's going to look on your homework, and they'll just have the box after this. Okay. So the two things we have to look at, and these are some of the examples I think that we did earlier. The two things we have to look at are the degree and the leading coefficient. So the first question I have, and be careful before you answer, what is the degree of this function? 3. Now, does everybody see that it's 3? Because this is not in the right order, is it? It's not in standard form. So the 3 comes from right here. And what's important about that 3? So we check out the degree. It is a 3. And what's important about that? It's odd, right? That's what we have to worry about with the degree. Does it fit into this group or this group? That's the question we're trying to figure out. And so since it is odd, we know it fits into this group, right? So that means it's either going to look like this, or it's reflected and it's going to look something like that, right? Those are the two options. Does that make sense? So then the other thing we have to look at is the leading coefficient. So what is the leading coefficient in this one? And again, it's not in the right order, so be careful. The -4. And the important thing about that -4 is it is negative, right? Which tells us which of these two should it be. The one on the right, the second one. It's going to be that one. Does that make sense? Because it's like this, but it's been reflected because of the negative. So here's how we fill in our blanks. We know that according to this, the left side should be up and the right side should be down, right? So which one is this asking about? Does it make sense? Negative infinity for the x's is the left side. So we want to say that this is going up. What do I have to put in here? Going up on the left-hand side, we want to put in positive infinity. Okay. And this is talking about the right-hand side. X approaches positive infinity. So again, we're talking about x's and y's. X's are left and right. The y's or the f of x is up and down. What's happening as we go to the right-hand side? It's going down. So what do I have to put here to tell us that it's going down? Negative infinity. Okay. And that's how we do this every time. It's got to be one of those four things. It's either even or odd, and then it's either positive or negative. That's all that we look at every time for these. Any questions on this one before we go to the next one? Okay, here's the next one. And this is the one that I was nice on, and I put it in the right order for us, so that was nice. And good, and we're going to look at the same two things. The first thing I want to look at is, what is the degree? 5, correct. It's this one right here. And what's important about that 5? It's what? Oh, yeah, I just didn't hear what you said. She got this look on her face. Oh, no, he's questioning me. I must have said it wrong. No, I just didn't hear it. So it's odd, which means, again, it's like this one, right? It's either like this one or it's reflected. So it's going to look like this, or it's going to look like this. Something like that, right? As far as the end behavior. That makes sense? So then we look at the leading coefficient. What is the leading coefficient this time? That is also a 5. And what's important about that one? It's positive, right? So the first one we're looking at for even and odd. The second one we look at is positive or negative. So this one's positive. And so which of these two is it if we have a positive leading coefficient? Has it been reflected or not? No. So that tells us it's this one because it's going to look like this, right? Okay. So then how do I fill out my answer? G of t is what it is this time. So as t, and we view them the same way as x's. So this is talking about the left-hand side. What is our function doing on the left-hand side? It's going down. How do we describe that? Negative infinity. Okay. And then this is talking about the right-hand side. What is our function doing on the right-hand side? going up. So we're going to put in positive infinity to describe that. Okay, and it's the same process every time. We're just checking, is it even or odd? Is it positive or negative? It's got to be one of those four. Okay, any questions on that one before we go on? All right. And I don't have a copy of those notes in front of me. Can I look at your notes quickly for a second? Okay, I'm going to change this one because all of these are too boring because they're all the same. So we're going to change this one, and we're going to make this a 4. Okay, we're going to make that a 4. And so now, as we look at this, what is the degree of the function? 4. It is a 4, right? And what's important about that is it is even, and that's why I had to change it because all of them were odd, right? So I didn't want them all to be odd. So, whoops, I just wrote odd. It's even. Okay, and that tells us that it's going to fit into this sort of a characteristic, right? Where they both go up or they both go down. Does that make sense? Then we want to look at our leading coefficient. What is the leading coefficient this time? -1 is correct because it's the number in front of that, right? So -1, and the important thing there is it is negative. So which of these two options will it be if it's a negative leading coefficient? The down. Yep, it's going to be this one. So how do we describe that? This, again, is talking about the left-hand side. So what do we have to put in here to describe that it's going down? Correct, negative infinity. And then the other one is also going down, right? So this one is also going to be negative infinity for both of them. That's right. Okay, is that making sense? Okay. So now if you see one of those, you're going to know what's happening on the left or the right-hand side. Now, let's see what we can figure out about this one based on its graph. Can you erase those? You've got them in your notes, hopefully. Okay, so what can we determine about the degree and the leading coefficient of the equation for the polynomial graph? Well, the first thing I would look at is the degree of this one going to be even or odd? Why is it odd? Because one side is going up and one side is going down, right? That's all you need for odd. If they go the same direction, we know it's even. If they go different directions on the left and right, we know it's odd. So we know the degree is odd. That's the first thing we know. And the leading coefficient. Okay, and what are we asked about the leading coefficient? Is it positive or negative, right? So what do you think about this one? Would the leading coefficient be positive or would the leading coefficient be negative? Positive. Why? Yeah, that's the normal one without it being reflected, right? So you're correct. Let me get a different color here. The leading coefficient is positive because it looks like that power function of the odd ones before it got reflected as far as the end behavior. It's down on the left, it's up on the right. Does that make sense? Any questions on that? Okay. So another term, and we've used this with the lines that we've been graphing and different things, is it's called horizontal intercepts. These are also called zeros or roots of the function. And that's going to be where it crosses the x-axis. It's also sometimes called x-intercepts or horizontal intercepts. They just use it in general because, you know, sometimes how we saw x's or t's or p's as the variable, it's not always x's. But in general, we tend to use x-intercepts there. So let's look at this. Given the polynomial function here, written in factored form for our convenience, determine the vertical and horizontal intercepts. So I want to think about what the graph would look like first, any generic graph. The x-intercepts are going to be right here where it crosses the x-axis, right? And if you think about the ordered pairs, the ordered pair points, x comma y, every one of these points that you think of that's on here will have the form of some x value, comma, 0, right? Because going up and down at all. So the second number will always be a 0. Does that make sense? So for the x-intercept, it's always going to be x comma 0, something comma 0. Now what about for the y-intercepts? Which would be these. So something on this point right here, on that line. So this one, the y-intercepts, anybody want to give me a description of that? What would those all kind of look like as ordered pairs? 0 comma something for y, right? Whatever the y value happens to be. And that's important for us because we're going to use that right here. Okay, so let's see if we can do this. Let's say we're going to find the y-intercept first. So y-intercept, we're going to put in zeros for all the x's. That's what has to happen for a y-intercept. So we're going to have, and I'm just going to write y instead of f of x. So y equals 0 minus 2, 0 plus 1, 0 minus 4. Because that makes we just put in zeros for all the x's. And then we do the math. What is 0 minus 2? Negative 2. What is 0 plus 1? And what is 0 minus 4? Okay. And then what does this mean since there are no symbols in between here? Multiply. So negative 2 times 1 times negative 4 is 8. So our y-intercept is 0 comma 8. Okay. Now, let's check out, is that one okay? Does that make sense for the y-intercept? How we did it, put in a 0 for the x's. And for the other one, we're just going to do the opposite because now we need the 0 to go for the y. So for the x-intercepts, we're going to have 0 equals x minus 2 times x plus 1 times x minus 4. And right at the end of class last week, we talked about what happens if you've got a bunch of things multiplied together equals 0. And we said, well, if x minus 2 equals 0 and you multiply by this, the answer will be 0, right? Or if this one is 0, the answer will be 0. Or if this one is 0, it will make it true and they'll all end up equaling 0. So the way we find these is we just take each individual factor like we did last week and we set each individual factor equal to 0. Does that make sense? It's the same reasoning that we used last week with quadratics when we were factoring. Okay, so what do we get for an answer here? What do we have to do to get that x by itself? Add 2, and so we just get 2. What do we have to do for this one? Subtract 1, so we get negative 1, and over here, add 4, so we get 4. Now, we do want our answer to look like this, right? As an ordered pair, we want to know where does it hit the graph. So this is x is 2, y is 0, just like we mentioned, right? The x value, comma 0. This one will be negative 1, comma 0. And what will the last one be? 4, comma 0. So notice there are, in this case, 3 x-intercepts and only 1 y-intercept. There can only be 1 y-intercept, but there can be more than 1 x-intercept. Okay? But there can only be 1 y-intercept. Does that make sense how we got those? To find the y-intercepts, you put in a 0 for the x. To find the x-intercepts, you put in a 0 for the y. And if it's already factored, it makes it nice because we just set each factor equal to 0. Okay? Some more characteristics of polynomials. That we have. A polynomial function with a degree of n, whatever that number is, a degree of n, will have at most n horizontal intercepts. So if the degree is 4, it could have up to 4 x-intercepts, horizontal intercepts. Okay, it can't have more than that. It could have less. So at most, whatever the degree is. An odd degree function or an odd degree polynomial will always have at least 1. The even ones don't have to have at least 1, but the odd ones do, because remember, they are up on one side and down on the other side, and somewhere they have to cross to get from one side to the other. The even ones don't have to have that, because if it's, you know, both going up or both going down and it's completely below the x-axis or completely above, then it won't have any horizontal intercepts. And then it has at most n minus 1 turning points. So again, if my degree is 4, that means it could have up to 3 turning points. And turning points means where it stops going up and starts going down. I think we talked about increasing and decreasing a while ago, right? I think I remember right. Did we talk about increasing and decreasing? Increasing means you're going up, decreasing means you're going down. So if it stops going up and starts going down, we call that a turning point. It's a very non-technical term, but it's a turning point, right? So it'll have at most 3 of those if the degree is 4. So look at this particular example. What can we conclude about the degree of the polynomial? Well, there's a couple things. The first thing is, what do we know automatically about the degree?
Even.
The leading coefficient will be positive, but the degree is even, right? So right away, we know the degree is even because you're going up on the left and up on the right. They're going the same direction. And you're correct. The leading coefficient would be positive because they're both going up. Okay? What else do we know? Well, the next thing is we can see that there are 2 x-intercepts, right? Which means the degree has to be at least what? If there are 2 x-intercepts, the degree has to be at least what? Well, that's where they are, but we're talking about the degree, and we're going back to, it has at most n intercepts if the degree is n. So if there are 2 x-intercepts, we know the degree has to be at least 2, right? Because it has 2 x-intercepts. Okay, so from the zeros tell us at least a degree of 2. Does that make sense? The zeros are the horizontal intercepts. Those are interchangeable words. Okay. But here's the one that tells us it actually has to be higher than that. How many turning points do we have? 3 turning points. And if there are 3 turning points, what do we know the degree has to be then? At least what? And of course, I wrote it in the way. You can't see it anymore. But it says at most n minus 1 turning point. So if I've got a degree of 10, I could have 9 turning points. If I've got 3 turning points, I know the degree has to be at least 1 more than that. The degree has to be at least 4. Right? Because if your degree is 4, you could have at most 3 turning points. So that may take a little bit of practice, but the turning points tell us, the 3 turning points tell us, the degree is at least 4. Okay. Is that the last one on your notes? Let me just make up one more example and see if we can figure this one out. So forget about that picture for a second. If I make a graph that looks like this, and let's say that I've got intercepts right here. Okay, if you can kind of see that, this keeps going up. Okay, what do we know about the degree of this one? First of all, it's odd, right? Because it goes down on one side and up on the other side. So it is odd. From the zeros, we see there are 3 x-intercepts or 3 zeros, so it has to be at least a 3, right? But what does this tell us when we have 1, 2, 3, 4 turning points? That tells us the degree has to be at least what?
5.
At least 5. It has to be one more than the number of turning points. Okay. So, and if we go back, and that's correct, it would have to be at least 5. If we go back to some of the ones we have done before, like our actual parabola, 1 turning point means the degree has to be at least 2. But you remember how at the beginning we saw a whole bunch that kind of looked like this, like x to the 6th power? I'll just say y. Looked pretty similar to this. So it doesn't mean that it has to have exactly 2. It just has to have at least 2. Right? I don't know. I maybe said at most last time. I meant at least. So the degree has to be at least 2, but it could be 6 or it could be 8 or whatever. So sometimes the shapes are deceptive, but what we know is it has to be at least 2. Okay? It might be bigger than that, but it's at least 2. Okay? That makes sense? So we talked about the power functions, which helped us talk about end behavior. And then we got into the degree and how big the degree would have to be. So I think that's it. You guys told me that was the end of your notes. You got 7 graded problems there. Please remember to do this assignment as well as if you haven't already done it, I haven't looked, but if you haven't already done it, make sure you do your factoring assignment from last week.